All right, y'all, let's get started. So last class we finished out chapter 15 on kinetics. So this class we're going to start in on chapter 20, which is electrochemistry. All right, we are coming down the home stretch. We got 2 chapters to go here. And actually that very last chapter, nuclear chemistry, we just got 1 lecture on. All right, so we got finishing out the end of the semester here. Our goal for this electrochemistry chapter is to understand what the heck is going on in this diagram here of a battery. Okay, that's what electrochemistry focuses on, or rather that's what a battery really takes advantage of, is electrochemistry. But we got to build up to that, all right? We're going to focus today on the components of a battery that are really important, which are the oxidation and reduction reactions that happen. So this is a specific class of reaction, okay? Oxidation reduction reactions. Often just called redox reactions. Okay, and these redox reactions are at the heart of electrochemistry because these are reactions where electrons are being exchanged between 2 elements. Okay, so a redox reaction is a reaction where electrons are exchanged. So we're transferring electrons from one species to another. Okay? Many, but not all, chemical reactions are redox reactions, right? Where electrons are being transferred, but not all reactions are like that. So for example, precipitation reactions. No electrons are being transferred. You're breaking bonds, you're forming new bonds, right? But this is a specific class where we got electrons moving around. So a very simple example would be if you took copper, solid neutral copper metal, and you tossed it into a solution of zinc chloride, something with these zinc ions. What you would get is solid zinc metal and copper 2 ions. Right? So my zinc is going from being a zinc ion to neutral zinc metal. Right? So is it gaining or losing electrons when it's doing that? Remember, electrons are negatively charged. It's going to be gaining electrons. So in this example, my zinc is gaining electrons. And my copper is going from being neutral copper to a copper ion. So then the copper is losing electrons. And this is always going to be the case with the redox reaction. You're going to have one species gaining electrons. Where did they come from? From something else that was losing the electrons, right? Electrons can't be created out of thin air. So if one thing is gaining electrons, something else has to be losing electrons. Okay? Losing electrons is oxidation. All right, and so to remember that, we use this acronym LEO. Losing electrons is oxidation. All right, so then the other thing, gaining electrons, that would be reduction. So here my copper is being oxidized and my zinc is being reduced. Right? The copper's losing electrons. Again, losing electrons is oxidation. The zinc is gaining electrons in this reaction. That is a reduction. All right? Now, because there's a transfer of electrons in these reactions, they're actually a deceptively huge pain in the ass to balance. This one right here isn't too bad. You could do it just like you did all your other strategy here, what we would call mass balancing. That's what you've been doing all the way up until this point. Okay? But some redox reactions are not so simple that you can just mass balance them and be done. We got to have this special method for balancing these reactions, and that's really going to be our focus of today. What's called balancing by half reaction. All right, and why we have to do this, why are we going to learn this whole new process for balancing chemical equations? Again, it's specific to these redox equations, and that's because balancing by half reaction allows us to keep track of those electrons that are being exchanged. Okay? So let's take a look at a chemical equation here. I'm going to leave some space because we're going to put some rules down. So here's our sample chemical equation here. We have an iron ion. Reacting with a permanganate. There's an iron 3 ion. And a manganese ion.
Would the manganese be +2 or -2?
Manganese is +2 on the product side. Because it's a metal, so it forms positively charged ions. Unless it's a polyatomic ion paired with oxygen, it's going to be positively charged. Okay? So here's this chemical equation, and we have to balance this chemical equation. So right off the bat, we see that something's a little different than what we've seen up until this point. Why is there an oxygen on the left-hand side and not on the right-hand side, right? Like, what the heck is going on here? So this is a very common way of displaying these redox reactions, is kind of simplifying things down. Okay, but when we balance, we're going to have to account for that. All right? Again, the big thing also is that it's going to help us keep track of our electrons that are being exchanged, and we'll see that here in a second. I will say this, all of these are aqueous. I'm going to get real lazy at this next step and not bother to write my states of matter anymore. We just keep in mind that everything is aqueous here. Okay? So, balancing by half reaction. The first thing we're going to have to do is actually split this chemical equation up into its two components. Okay? So we're going to split chemical equation into what are called half reactions. So on the one side, I'm going to have my iron 2 going to iron 3. Right? Notice that that's the difference between reactants and products, is the charge on that iron ion. And the other half reaction here is going to be my permanganate ion becoming manganese +2. You can already see. Okay, so we split this into these half reactions, and we're going to kind of treat these half reactions separately. Okay? So our second step is to mass balance everything except the hydrogens and oxygens. All right? So we need to do this for both of our half reactions. So let's just zoom in here. I need to make sure I have the same number of ions on the left-hand side as I do on the right-hand side. Right? So do I have to change anything here? No, in this case, I'm cool, right? Everything's mass balanced here, paying attention to those elements, everything other than oxygen and hydrogen. And what about on my other side here? Do I have to change anything? Again, we're going to ignore the oxygens for now. Are my manganeses mass balanced? Do I have the same number of manganeses on both sides? Okay, check, check. That's step one. Step two, or rather step three, we're now going to balance the oxygens adding water where necessary. Okay. So on this side, do I have any oxygens to worry about? No. All right, cool. So now let's jump to this side, though. I need to mass balance these oxygens by adding water. So which side am I going to add water to? My product side, how many waters am I going to add if each one is H2O, has one oxygen? 4. So I'm going to stick 4 waters on there. All right, and now it's like, all right, great. Well, I balanced my oxygens, but now I just threw another element into the mix here, the hydrogens, and now they aren't balanced, right? So our next step is we're going to balance hydrogens. By adding H+ ions. Okay. So I don't have to worry about anything over here. There's no hydrogens or oxygens. I kind of don't have to do anything with that side. But over here, I'm going to have to add some hydrogens. Which side am I going to add my hydrogens to? The left-hand side, the reactant side, right? And how many H+ ions am I going to add to balance everything out? 8. Okay, so now everything is mass balanced. I have the same number of hydrogens, oxygens, and manganeses on the left side as I have on the right side. Okay, and now is this really crucial step for these redox reactions. We're going to charge balance these half reactions using E-, using electrons here. So what the heck do I mean by charge balance? Let's look at this half reaction here. What is the net charge on my reactant side? +2. And what's the net charge on my product side? +3. So these are not charged balanced. I have a different net charge on the left-hand side as I have on the right-hand side, and I need them to be the same. Okay? And what I'm going to do is add electrons in order to balance these out. And of course, electrons have a charge of -1 in particular, right? So I'm going to add negative charge. So in this case, if I add an electron over to my product side, now all of a sudden the net charge over here isn't +3, but +2, and everything is charge balanced. Right? So by adding electrons, I've made sure that the net charge is the same on both sides, on my reactant side and my product side. Okay? So that's what we mean by charge balancing. All right, let's go over here. Let's do the product side first because it's a little easier. Water is neutral. So if I have one manganese ion, what's the net manganese 2 ion? What's the net charge over here on my product side? +2. All right, now this one's going to be a little tricky. I have 8 hydrogen ions. Each one has a charge of +1. And then I have this one permanganate ion that has a charge of -1. So what's the net charge over here on my reactant side? 7. So everybody take a second and see if you can't charge balance this chemical equation, or this half reaction rather, by adding electrons. All right, so which side am I going to add my electrons to? I'm going to have to add them to the left, right? Because electrons are negatively charged. And how many do I add? 5 electrons. Now when I look at the net charge on this side of my reaction, it's +2, right? I got this charge balance now by adding those 5 electrons. Okay, so now we're going to be able to stick these things back together. Okay, we're going to combine these two half reactions back. But we got to combine them in such a way that our electrons cancel out. All right, so to make a little bit more space for myself, I'm going to stagger these here. So let me pull this half reaction down here. All right, so actually before we go on, I want you all to try to think. One of these half reactions is our oxidation half reaction. The other half reaction is our reduction half reaction. Given what we discussed at the very beginning of class, I want you to try to figure out which one's which here. Right, remember, what's that acronym? Leo. So losing electrons is oxidation. Which half reaction represents the element losing electrons? The one on the left or the one on the right? Left, right? So this is my oxidation half reaction. This is my reduction half reaction. Okay? And again, I want to sum these two up. But in order to do that, I have to have my electrons cancel out from my final reaction here, from my net reaction. The problem is if I summed them up right now, I only have 1 in my oxidation reaction, but I got 5 in my reduction reaction. Okay? So what I'm going to have to do is take this oxidation reaction and multiply every component by 5. That way I have the same number of electrons in both. Right? But it's not just going to hit those electrons. Now I'm going to have 5 iron 2 ions, 5 iron 3 ions, and 5 electrons. All right, again, my goal is to combine this into one balanced chemical equation, but in order to combine it, I need those electrons to cancel out. I need to have the same number on both sides. So in order to do that, I'm going to multiply this reaction, the whole thing, by 5. All right, and now I can combine. Everything on the reactant side from both is going to be on my reactants, so we'll add these two together. So I have 5 Fe plus 2, 5 electrons, 8 protons, and that permanganate ion. All right, that takes care of all my reactants. Now I'm going to jump to the product side. 5 iron 3 ions, 5 electrons, that manganese 2 ion, and 4 waters. All right, and now I can see, and this was my whole logic, is what cancels out from this? Those 5 electrons, right? I got 5 on both sides, and that has to be the case. In order to have your balanced redox reaction, you can't have any electrons appear in your final overall equation. Okay, and now notice that if we had just taken this, even if we added the waters and the hydrogens and all that jazz, there would have been no way for us to know that we had to have a 5 here if we just mass balanced. Right? The only way we got that 5 is by balancing those electrons, that charge balancing step. And that's the key to these redox reactions. That's why we have to go through this pain in the butt procedure of splitting it in half so we can make sure that we have the correct number of electrons in our redox or in our oxidation reaction as we do in our reduction reaction, that we're charge balanced here. Okay? So that's why we got to go through this pain in the butt step for these oxidation reduction reactions. All right, so just to be clear, my net reaction here, just to cross out, basically just this exact same thing, but with those electrons canceled out. All right, so this is my final answer for my balanced chemical equation of this reaction. All right, and notice how I have these hydrogen ions, these protons that appear in my overall balanced chemical equation. So does this mean that this reaction would be taking place under acidic conditions or basic conditions?
Oh, acidic.
H plus, right? Acid. Acidic conditions. So this would be balancing this half reaction. This would be specifically under acidic conditions. All right, so in terms of our rules here, these are for acidic conditions. All right, so you may or may not see where we're going here. Now we're going to do the same thing, but under basic conditions. But it actually starts off, the first few steps are the exact same, up into this fourth step here. All right, so I want you guys to try to do this on your own as best as possible. Let's do another example, chemical equation. Got an iodide ion combines with, again, we got our permanganate. But under basic conditions, we get solid iodide or solid iodine. All right, so here's this chemical equation that you're going to balance for me here. See if you can't get those first four steps down, given what we did previously. All right, I'm going to give you all a few minutes to go on your own, and then we'll come in and do it together. All right, so let's do this together now. So I'm going to split it up into these two half reactions. My iodine's on one half reactions, those manganeses on the other one, and we're going to treat these two separately. Okay? Step one is going to be to mass balance all the elements except hydrogen and oxygen in each one of these half reactions. So what do I got to do over here on this half reaction? Is it balanced?
Yeah. No.
No. So what do I got to do? I got to put a 2 out front of that iodide ion. So I have 2 iodines on the left and 2 on the right. All right. Over here, again, I'm going to ignore the oxygens at this step. Are my manganeses balanced here? All right, cool. So this one I don't have to do anything on step 1. But make sure you can see that on step 1 on this side, I have to put a 2 there. All right, now I'm going to balance my oxygens by adding water. I don't have to worry about it here. I do over here have an imbalance in my oxygens, right? I got 4 on the left and only 2 on the right, so I'm going to have to add 2 more waters over here. Okay. And now I'm going to balance my hydrogens by adding protons, hydrogen ions. So I'll need 4 over on this side. Okay, so again, those first 4 steps, just like we saw before. All right, but the problem is under basic conditions, I can't have this thing in my final answer, right? This will not survive under any sort of basic conditions. So I got to get rid of that. So how are we going to get rid of that? We're going to add a step here. This is the step that's specific for basic conditions. We're going to add hydroxide to both sides in order to cancel out those protons. Okay? So I don't have to worry about it over here because I don't have any H pluses. But over here, I need to get rid of these H pluses. So I'm going to add hydroxide ions to both sides to cancel them out. And we got to do it to both sides. Otherwise, we'll mess up our balancing. Right? So over here, I'm going to add 4 hydroxide ions. And I'm going to do the same thing over here. I'm also going to add 4 hydroxide ions. Okay? Now, if I have 4 hydroxide ions combining with 4 protons, let's go back to semester 1, acid-base chemistry. What is this going to form? Water. So this will form 4 water molecules. Right? Hydroxide will react with hydrogen ions to produce water. So that's how I'm able to get rid of those protons. Make everything the same color. All right, so again, this is this step that's a little weird. For the basic conditions, we got to get rid of these hydrogen ions by adding hydroxide, but we got to add the same number to both sides so we don't mess up our balancing. And then from here, we're back to regularly scheduled programming. Now we're going to charge balance using the electrons and then combine in such a way that we cancel out those electrons. Okay, so take a second and see if you can't charge balance these half reactions. All right, so let's look at this half reaction here with our iodine. What is the net charge over here on the left? If I have two iodide ions, each one has a charge of -1. That's a total of -2. And what about on the right-hand side here with my one neutral iodine molecule? 0. Okay, so I'm going to charge balance by adding electrons. That means I need to add 2 electrons over here on the left, so that over here on the right, so that my net charge is -2 over here as well. So then is this the oxidation or the reduction half reaction?
Oxidation.
This is the oxidation. Right, so notice oxidation's losing electrons. So oxidation means that electrons are on the product side. All right, let's go over here. Charge balance this business. Four neutral waters plus 1 negatively charged permanganate ion, charge of -1. What about the net charge over here? -4 because of my 4 hydroxide ions. All right, so that means I'm going to need to add 3 electrons to my reactant side. All right, so we said oxidation. The electrons are on the product side. Reduction, electrons on the reactant side. And this is a great double check when you're balancing this chemical equation, when you're charge balancing. One thing has to be oxidation and the other thing reduction, right? So you know you've charged balance. One way you can tell that you've charged balance correctly is if you've added electrons to the product side of one and the reactant side of the other. If you're adding it to the reactant side of both of them, something went wrong somewhere, right? It's always going to be on the product side of one, your oxidation half reaction, and the reactant side of the other half reaction, your reduction reaction. Okay, so now I got these things charge balanced, and I need to combine them in such a way that those electrons cancel out. All right, I got 2 over here and 3 over here. How the heck am I going to do that? I'm going to go for what's, if we're being math nerds, their least common multiple, right? So I'm going to take this half reaction and multiply it by 3, and this half reaction and multiply it by 2 to make them both 6, the least common multiple of 2 and 3. right? I can't turn a 2 into a 3. I got to turn them both into 6. All right, and remember, that means that you multiply everything in there by that 3, for example, for our oxidation half reaction. So that means I have 6 iodide. When I go to sum this up, I have 6 iodide ions plus 6 electrons, 8 waters, and 2 permanganates. Jump to my product side, 3 iodines, 6 electrons, 2 MnO2, 4 waters, and 8 hydroxides. All right, sum everything up. All right, and again, we went through great pains to make sure that our electrons cancel out. What else can I simplify here? What is it? The waters, right? I got waters on both sides. I got 8 on the reactant side and 4 on the product side. So I'm going to get rid of these 4 and take this down to just 4 waters over here. Right? We want to simplify when possible. I got waters on both sides, so I can simplify. So my final answer, 6 iodides, 4 waters, and 2 permanganates. Give 3 iodines, 2 manganese 4 oxides, and 8 hydroxides. All right, here is my final balanced chemical equation for this redox reaction. All right, so given these sort of unbalanced redox reactions here, in order to balance them, we actually have to split them in half and do this balance by half reaction method, because that's what's going to allow us to keep track of the electrons that are being transferred. And it's really important that we pay attention to that, because that's the whole shtick of a redox reaction, the transfer of electrons, right? Cool. All right, so we'll pick up with this next time. And again, our goal is to better understand that figure of that battery. That's our goal for next class.